Okay, as we're just getting, I think people will still be signing on here, but I want to thank my co-conveners here, Xiaoxing Ji, who will give the next talk, and Bobby Jackson and Israel Silber, who will share some of their work on forward simulation with us. And Scott Collis, unfortunately, had to be at another breakout that's happening right now. Thanks to Sally and the program for putting on a great meeting and providing this virtual space. And thanks to you all for attending. So let's see, we got about 1 more minute. So I'll just mention that for the first hour, and it's going to be a scant hour, I think, we're going to have some three brief overview presentations, and we can take a few questions after each of those. And the second hour is intentionally open discussion. And I know that can be a little bit harder in this virtual framework. So we've left some, reasonable time to do that. So as we go along, if you could type in your question to the chat or the Q&A. Actually, Israel will be monitoring that as for the first 2 talks at least. Israel, is it better to go with Q&A or chat?
For the talks, I think Q&A.
Okay, thanks. So please type in any questions or comments on the Q&A, and Israel will help. I won't try to monitor that while I'm speaking, and we won't expect speakers to do that, but the moderator can help us raise some of those at the end of each talk. And you can also raise your hand if you'd like to ask a question, and moderator will be looking for raised hands. I'll moderate the third talk, Israel. And then from a phone, if you're on the phone, and thanks to those attending on the phone, you can toggle *9 to raise your hand. Obviously, you won't be able to use Q&A, but please do that. And third, during open discussion, maybe it's possible for us to share video just to indicate that, we're still, you ask a question and you maybe want to respond again and so on. Feel free to turn on your video for that. Please keep questions and comments as brief as possible, just so that we can accommodate as many as possible. And finally, this session will be recorded. So it's 11:01, and I think I'll go ahead and get started. So the title of my slides today is in the form of a question and an equation. So LES-SEM based on well-observed case studies plus evaluation of Earth system model physics using long-term ARM data. And the question is that a good pairing for community participation? We're working towards that pairing at NASA GISS in our climate model physics development now, and I'll show an example of that. And we are doing this in a way that someone else can pick it up and use it. So our question is there interest in that model maybe for topics other than polar clouds, which is just the example I'll give today. So where's this, where's this coming from right now? Why this session now? And I am the current chair of the relatively new ARM Cloud and Precipitation Measurements and Science group. And that group has the charter that is asking how resources can best be applied, ARM resources, to increase the scientific impact of ARM measurements. And Jim Mather, to whom this group reports, it's just a community recommendation group, basically. He asked us specifically, are there subtopics where ARM has strong potential to contribute, but is not reaching that potential for various possible reasons? And we put our heads together and came up with some various recommendations and brought these to the last PI meeting where we got some feedback. And one of those recommendations, which this breakout addresses, is that we suggested seeking and supporting frameworks that bring individuals and groups together for limited joint exercises. And our idea here is this can lower the bar for participation. So not every group has to develop its own case study from a field campaign, but if that is the intention to do group activities, it can affect how that's done if one group does it, for instance, I would argue. Anyway, to discuss. So examples of this such exercises are obviously the GCSS model intercomparison studies. And many of these cases were based on ARM data, a majority, I think, and they're still widely used. And we're using many of these at GISS in our development. A second example is the GAS. GAS is the follow-on program to GCSS, and again, GUX program. And Xiaocheng is leading the diurnal cycle of precipitation project, and he'll give us a brief overview of that next. And the topic here is, again, just kind of an opening question, is a general pairing that to some extent is in that DCP project. And in the example I'll give today, is this generally a good pairing to pair these case studies with use of long-term observations to evaluate free-running model physics. So the latter usually require a forward simulator approach, and we'll hear something about that in the third talk. So briefly, our Model E3 development approach in our latest development at NASA GISS has been on the stratiform cloud physics side, which is mostly what I'll be talking about today, has been led by Andy Ackerman. And we have heavily relied on LES SCM comparisons, and they're almost exclusively, but not entirely, based on field campaigns. And then we went through a climate model tuning process that was led by Greg Elsacer and Marcus Van Leer-Walke using machine learning that was based strictly on global satellite data sets. So this is kind of a two-step process. And at the LES SCM stage, we loosely developed parameter ranges for the stratiform and convective cloud physics parameters that were used in the tuning exercise with the satellite data. By the way, roughly half of those were stratiform scheme tuning parameters, including dynamics, and then the other half are convective scheme tuning parameters. And what came out of that, by the way, is that we came out with 4 model versions, actually, with estimated ECS values between about 3 and 4.5K. That we consider kind of equally defensible. And we plan to submit those to CMIP 6 as soon as possible. So our field campaigns, or the use of the LES and SCM framework, cover these case studies that I'm showing here. The first few are dry boundary layer cases, and then marine clouds, a continental cumulus, and two mixed phase cases that I'll discuss next, and then one deep convective, tropical deep convection, and one cirrus case. So for polar clouds, 2 of the GCSS cases that received quite a lot of participation were the MPACE and ISDAT cases. And MPACE is kind of famous for the diversity of model results. And I'm showing just one figure from Steve Klein's 2009 paper that included LES, CRM, SCM, a wide range of models. And for the baseline simulation, informed by measurements, the models got a wide range of ice water path and liquid water path. And I'm not showing it here, but even just looking at the CRM models, there was more than a factor of 4 difference in the liquid water path when all the ice microphysics was turned off. And this is for a deep cold air outbreak, kind of quasi steady state condition. I'll show you our model results for that shortly. So that was humbling, to say the least. And the next 2 intercomparisons, one based on Sheba, led by Hugh Morrison, and the next based on the ISDAT campaign, led by Mikhail Ovchinnikov, basically worked to constrain the ice microphysics. In the ISDAT case, I'm showing on the right here, results, we can see that without ice, and now only LES models are participating here, all the models are now getting a liquid water path, as shown in the blue on the x-axis on the right, all getting liquid water path within about 20%. So we didn't see that huge baseline spread even with the ice microphysics off. And I'm not sure exactly why that is. So we're seeing good agreement there. As we turn on the ice microphysics, diversity increases a little bit in liquid water path, But the models are still, well behaved compared to the MPACE case, because the ice nucleation, ice properties, ice growth rate, ice fall speed, everything was quite tightly constrained. And the paper also identifies the main difference between the bin simulations with the right and left, with the highest ice water path here shown with the highest ice number concentration, highest ice nucleation. The difference between those models when they were using 2-moment versus bin microphysics, the paper identifies a dependence on basically the fact that the bin models are not producing exponential size distributions. And you can see the bin models agree with each other as well. So we really converged the results quite well. So I guess we use this case to develop our schemes and work on how our schemes, macrophysics and microphysics, are working together. And here we're using the Brotherton and Park moist turbulence scheme and a modified version of the Morrison and Gettleman 2-moment scheme with prognostic precipitation. And I want to show you on the right here, just briefly, the PBL height. And this is for a series of, I'm showing the LES, a baseline LES in black. And I won't go into too many details here, but these going from red to blue to purple are our SCM with increasing ice crystal number concentrations from 0.1 per liter to 10 per liter. And we can see that 1 per liter, this is cloud ice, is achieving something similar to the LES, and that's similar to the ice number concentration, the LES, when we look at the ice water path second from the bottom on the right. And our liquid water path at that point in the blue simulation is rather similar to something with vanishingly little ice, which is shown in red here. And the model can basically maintain with this setup a deep boundary layer on the left, about 1,500 meters high. And this is, this doesn't mean that the climate model can create this. The model is initialized with this in SCM mode. At least it can maintain it. And it can maintain this with the physics shown. I won't go over all the other parameters here, but so this was a last note is that when we get a really high ice number concentration in purple, the boundary layer essentially collapses, and you can see that in the turbulence parameter in the second from the left. So yeah, so that's, let's see, and then it goes into a convective state. So I'd like to say a little about the other case that Israel developed working with us using the AWARE campaign data over Antarctica. And unlike MPACE, we didn't have such a beautiful in situ data set, but I think we nonetheless really learned a lot about this. And so I want to briefly step through the physics the unique physics that we think this test gives to our model. So this is a Lagrangian simulation with the LES, and we're starting in a cloud-free state. And I'm sorry I'm not fitting the time series on here, but in the lower right, second from the right, is shown the theta E profile. So this is a stable initial profile, and the TKE on the right is 0 until about hour 14, when we develop a turbulent layer that's driven by cloud top turbulence. And the way that happens is, in this case, we have a little bit of ascent that leads to, as of hour 5 on the upper left, on a log scale, a little bit of liquid water content. As that layer cools, shown second from the left on the bottom, and I guess I can use my pointer here. As that cools, that drives more condensation of liquid water, more cooling, more condensation of liquid water, a positive feedback that eventually leads to a turbulent layer, as shown here. And this simulation, we kind of arbitrarily end at 9 hours, which is close to our observed state. And in this JGR paper, we compare results to the observations. So this layer fails to fully deepen. It encounters a very stable layer near the surface. So we have this elevated turbulent layer, and this kind of birth of this mixed phase cloud is simulated. So we initially did that work to look at drizzle formation, and I didn't highlight that in the figure just now, but we think this is actually a great test for how a lot, maybe the majority of polar clouds in stable atmospheres are formed. And so we're pretty surprised, or I was pretty surprised, how well our SCM performs. And I'll just point to the liquid water path first. And I won't say too much about aerosols and other things because there is some sensitivity to that here. But anyways, for a case where we're activating a reasonable number of aerosol in both the LES and the SCM, liquid water path evolves in SCM with no ice at all in red, and 0.1 and then 1 per liter. And I guess I'm actually using INP here, but it's the same. Okay. So what we see here, again, no ice in the case with in red here, and on the left, I'm showing at 9 hours this elevated layer. So it's shown a little bit deeper in the SCM than in the LES, which is in black, but the liquid water content is quite well matched, and the liquid water path is quite well matched. So this is a pattern. I'm actually not sure that we see this a lot with our turbulence parameters. So we probably need to think about this a little more. And we're still in the process of preparing this for publication. So this was really helpful for us to understand whether our model can do a basic coupled mixed phase boundary layer cloud, whether it can do formation of an elevated decoupled boundary layer. And so I want to suggest a few pros and cons to this approach of using LES and SCM case studies. They provide a basic test of Earth system model column physics, just run by itself. It's a convenient framework for model development. It can be used to tune model parameters, and I would point to some really nice work by the French groups in using this to actually tune their parameters directly, all of their parameters, whereas we did this in the second stage using satellite data. I believe that observation-derived cases also highlight really fundamental knowledge gaps. We kind of can't get away from them, which is good, which includes ice multiplication, mesoscale structure, CCN and INP budgets, and so on. So what are cons, though? One is, how do you choose a particular case? Should it be statistically representative somehow? Or should it be maybe more representative of an extreme? In the case of the AWARE case study that I just showed, we wanted to confirm that our model could do a highly supercooled drizzling case. And so that's more representative of an extreme, I think. Is it good to do an ensemble instead? Is that required? Also, so this is kind of an open question. It kind of feels like it's never enough. Second, are improvements borne out in the free running model? And that's not obvious to me. And so I think we can also be sure that they're useful, but not sufficient. So something that could go further then is the use of ground-based long-term observations to constrain model physics and in a free-running Earth system model. And so an example that we're working on also from using AWARE data is cloud-based precipitation rate from supercooled clouds. And what we find in this work that Israel just recently submitted is that the great majority of supercooled polar clouds are precipitating at cloud base. And over the North Slope of Alaska, we think this is about pushing 90%, and a little lower frequency over McMurdo, but still extremely high. And we view these as lower limits because we see evidence that of precipitation that's not detected at cloud base in systems that are likely still precipitating but weren't counted in the methodology we used here. So we know that these are pretty poorly observed from space. It's hard to observe really light precipitation rates. And these ground-based long-term observations also offer us ancillary data. For instance, liquid water path, which is really useful in the case that we are looking at a single layer cloud, for instance, you can get a lot more information. For instance, on the bottom right is shown statistics from the North Slope of Alaska, where we have more than 7 years of data, so much better statistics. We can see that at every cloud top temperature, nearly, or almost all the cloud top temperatures, the cloud base precipitation frequency is greater than 80% consistently. And on the upper right is shown a PDF of cloud-based precipitation rate, really low precipitation rates that we argue is a good target for models from these long-term observations. And obviously this is not something we can get from just one case study, although I will say that all the widely simulated case studies do exhibit light precipitation rates. So putting the parts together, for us at GISS, we're working on this polar cloud pairing where these Arctic and Antarctic LES-SCM basic tests of our supercooled cloud persistence and decoupled cloud formation are tested. We're working towards evaluation then of our climate model with respect to its supercooled cloud occurrence frequency and associated with that, the cloud-based precipitation rate using these long-term Arctic and Antarctic data sets. And we expect that our SCM and our Earth system model performance will be related. So there are tunings, for instance, that break our SCM cases, and we would expect to see performance decrease in our full free running model in those cases. But we're still working towards that, so to be determined. So obviously other pairings or additions could be made, and I think I'll leave this for the discussion, but obviously warm cloud precipitation statistics are extremely well observed, I would argue, at the ENA site. And it would be interesting to also look at not just at the performance with respect to particular metrics we think are important, but also potentially the relationship of that performance to things we care, bigger things we care about, equilibrium, climate sensitivity, however that might be defined, or MJO in the case of deep convection or whatever. So this is my last slide, and then I'll pass the mic to Xiaocheng. So group activities on the GCSS model, a few pros and cons, just in my own opinion. So some pros are that there's reduced duplication of effort in setting up cases. I think there's also, in my experience, been a valuable consensus building and knowledge sharing regarding choice of cases and how to set them up. And if a lot of people are interested in a given case or a given data set, I think that can motivate and efficiently used dedicated efforts from observationalists to produce additional products. There are some cons, and these are not insignificant. It's really, in the past, in the GCSS model, there was really a major effort from a lead organizer, and we'll see that from Xiaocheng next, who has usually, historically, not really been specifically funded to do that. Second, there has often been a pretty big overhead on every group who participates to report some specified results and file formats, and I absolutely cringe when I think of all of the diagnostics I requested when I ran the TWPI Center comparison. So thanks to those who participated. So what are some possible changes that could address some of the cons? One thing is that we could introduce community code development. For instance, to convert outputs to a unified format, we could provide Python code that ends with the unified format, and it makes it easier for people to produce the unified format output. As well as input for LES and SCM. So obviously there would be a little front end work by the group, but to the extent that repeated different studies use that the same unified format, that could lower the bar or ease participation. Other aspects of community code development could be applying forward simulators with assumptions that really well match each person's model physics. And something that we didn't have before is community code that could plot results from multiple models versus observations. And that would involve having things on the same server, and I'll get to that shortly. As far as the LES and SCM component, I would like to point to the DEFI input-output community standards that were really nicely promoted in a workshop last week, and I attended this last Monday, and there's really a lot of interest from across all the US groups, and this came out of the French community, where their weather models and, you know, every weather to climate, they're all using this approach together for physics development, and I definitely saw interest there in all the US models in a similar way. So if this, if to the extent that future community activities happen at ARM, obviously it would be great to use a standard wherever possible. And second, we could introduce use of ARM computing resources. So for instance, I don't know, I think this is not widely used right now, but we have public availability now of ARM computing resources. This means we can all upload SCM results, LES results, and we can plot them against one of others' results using, you know, common Python GitHub codes. And that's not something we had readily available to us before. Third, we could emphasize a bare minimum package of runs and diagnostics and really include a low overhead participation option to really try to make it, quote, you know, cheap, inexpensive, easy to participate, as easy as possible. And lastly, it occurs to me that we could decrease emphasis on an omnibus manuscript. With many of the intercomparisons, groups, after they participated in the intercomparison, they went home and did their own studies in a variety of ways. So those cases were used for a variety of follow-on studies. And maybe there's some argument that that a really big manuscript where you wait for absolutely everyone's results and so on, maybe we could de-emphasize that. So I think I speak for all of us, and especially me and Xiaoqing, who've been around for a while doing these things, that we're more opening a discussion than proposing a solution. And with that, I'll pass it to Xiaoqing.
Just a second, Anne. There are a few questions.
Sure.
We have a question: do the new models with constraints also do better with MPACE and Shiba?
Do the new models with what?
Do the new models with constraints now also do better at MPACE and Shiba? Do they perform better with these RTKs?
Okay, so I actually did not impose, the only constraint I imposed there is the ice crystal number concentration. So that's a good question. And actually Steve Klein and I recently discussed that we would love to see MPACE done again by the same community. And I think we would see a lot of improvement. I don't know.
And another question, what are the quantitative limits of SCM LES comparison to observations? How much of the observation model mismatch is owing to forcing or environmental uncertainty?
Yeah, so as an LES modeler, I was always really uncomfortable with adopting LES as any sort of truth. You know, because we know, well, we saw in the liquid phase ISDAC case, for instance, you know, say 20% difference in liquid water path. If you look at, you know, a variety of quantities, we will see that type of diversity. And what changed me into someone who was willing to accept LES as good guidance, let's call it that, is working on climate model physics. And so the climate model physics is really, you know, challenged. Our model couldn't, you know, didn't have moist turbulence, couldn't maintain a deep boundary layer, and it took work for us to get everything working together, right? So I think at that level, we're talking, you know, not a 20% difference, but more like that factor of 4 or 5 difference. And so at that level of guidance, I think the OBS, you're not comparing the SCM to the OBS at that point, you're really comparing them to your LES. And for us, we have always had a first study that was a really close comparison of the LES with a variety of sensitivity tests to the observations. And the observations, 20% is not, you know, a not uncommon low end of observational uncertainties. And yeah, the uncertainty in the large scale forcing is just huge. So yeah, enough said.
Yeah, we're a little bit behind schedule, and there's just a final comment from Richard Forbes that having a minimum package of runs or diagnostic can be great to get wider participation. Some groups really want to participate, but have little resources to devote to it. So he would definitely recommend having different options for participation for each new group activity.
Great, thanks. Thanks, Richard. Thanks for coming. And I hope we can discuss further. And sorry, I took a little longer. So I'll pass it to Xiaoqing. Thanks, Israel.
Sorry.
Not at all.
Okay, thank you, Anne. So as has been shown in Anne's talk, pairing the case study with the long-term evaluation of the global climate model can greatly help, the climate model development. So in this talk, I'm going to provide an overview on an ongoing gas multi-model intercomparison study project that emphasizes on using such an approach to improve the modeling of diurnal cycle precipitation in both weather and the climate model. So this project is co-chaired by Xian Ma from Livermore, Peter Benchtold from UCMWF, and also David Nealon from UCLA. We include both a single column model component and also GCM component. So Shuai Jitang from Livermore is leading the SCM component of this project. So why we emphasize on the diurnal cycle precipitation? As we all know, the current weather and climate model continue having problems in simulating the diurnal cycle of precipitation. The problems specifically large over land. Here I list a couple of common problems. One is the rainfall usually occur too early after sunrise and too frequent, too vague. This is a well-known climate model problem in simulating such a feature. And also most of the models fail to capture the nocturnal peak observed in many areas, like over the southern Great Plains. They also fail to capture the transition from shallow to deep convection. And also they have very poor interaction between convection and the environment. And also there is no clear improvement when you increase the model horizontal resolution. So I just used this figure to show one of the problem for model to simulate the diurnal cycle precipitation. This figure shows the diurnal cycle of precipitation simulated by the CMAP models, which indicated by the green lines, and also the E3ISM with different convection scheme. This used in different colors, and then compare with the arm observation. You can see in the arm observation, the diurnal cycle precipitation peaked at midnight. So this is associated with the mesoscale propagation from west to east. So this is a well-known feature observed in the observation, but none of the climate model, including E3SM with different convection scheme, can capture this nocturnal peak of precip. So there's something actually we probably need a group effort to really understand what's going on with the model, any missing physics that could be identified from a group activity. So that's why the goal for this study is, to evaluate how well the current weather and the climate model simulated the diurnal cycle of precipitation over different climate regions. And specifically, we would like to understand what processes control the diurnal cycle variation of precipitation in observation and also in models. We try to identify the deficiencies and the missing physics in current GCM to really gain insight for further improving the parameterization, particularly for the convection in GCM. So we emphasize on 4 research topics, the nocturnal convection over land, and also diurnal cycle convection over ocean, convection transition, and also interaction between convection and water vapor. We try to understand, what physics that control all those observed behaviors. The approach we use is the hierarchy modeling approach that including both the single column model, cloud resolving model, LES. We also include the regional model and the convection permitting model to see, because they can run much higher resolution over a quite large domain. Then we see, how model behaviors when specifically relevant to the model resolutions. That also include the weather and climate, global climate models. So this approach has been proven to be very useful to bridge the scale gap between the field content data, such as ARM observations and also GCM model development. So this approach has been widely used in both the ASR ARM community and also the GAS community. In this study, we emphasize on both case studies and also statistical analysis. The case study actually really helped us to understand, the processes in much more detail. The statistical study gave, we can build up some, the model robust statisticals in some of the model pairs. Then we link both together, try to improve our understanding of those model problems for future improvement. The model simulation includes both short-range handcuffs that really help to isolate the model problems to help better understand the origin of the model errors. And we also include the free-running climate model. This for the GCM part of the study. We try to improve our understanding based on both observation and also modeling tests. We also apply some process-oriented diagnostics, such as the convection on-site diagnostic, to help, the model, to help analyzing the model simulation results. Currently, we have more than 20 modeling groups that have expressed their interest. That's including many single column models and also GCMs, but we also have a few, CRM and LES model, and also the limited area model and like MMF, and also global cloud resolving model. They express their interest, but we have not received, results from most of them. We already start to receive simulation results. Here, at least, we currently have, 9 single column models without 1 CRM and also GCM. Those participating models, including the model used in many major climate centers around the world, such as the ISRSM, NCAR model, and also ECM, WF, Met Office, their weather and climate models. And also some of the models used in different research groups, by testing different new ideas, particularly on convection schemes. So they also participate in this study. This really gave us a wide range of model and also parameterizations, emphasis on simulating dynamic cycle precipitation. That really can provide a lot of information by doing those cross-model intercomparison. The experiments we emphasize on both case study and also multi-model simulations. For the case study, we use the ARM case, both middle latitudes such as MC3E and the Pecan. Pecan is particularly designed for understanding the convection initiation for those elevated nocturnal precipitation at the STP site around the STP area. We also use the Amazon case, try to understand how model perform over tropical environment. It's the case study, and for multi-model, for multi-year simulations, we run single column model for more than 10 years at SGP, and also for the entire period, the 2-year period for Go Amazon field campaign. GCM, we have a free running GCM simulations, and also multi-year 3-day handcuffs that cover those periods. So here I show some preliminary results we got from the analysis of single column model results for the multi-year runs. This figure shows how well the single column model simulated the dynamic cycle for those afternoon precipitation days at the SGP and also the Amazon region. For afternoon precipitation, it is defined by like the peak precipitation rate should be larger than 1 millimeter per day, and the peak hour should occur between 1 p.m. to 8 p.m. And also the peak precipitation rate should be larger than 1.5 times the precipitation outside this peak hours. So we define those as afternoon precipitation, then we generate the statisticals of the cycle precip for those under such a condition. You can see most of the model so trigger the convection too early, compared with the observation which showed as the black line. This is from the arm observation. You can see for both STP and also Amazon region, the model shows those. This is a pretty common model problem, but over the tropical region, you do see, the peak actually varies from, not like as STP, but over Amazon, it even varies from model to model over different, much larger time period. So this is one common feature we see from this. For the nocturnal precipitation days, if the day dominated by the nocturnal precip, is defined by similar like what we said, but the peak hour should occur from 0Z to 7Z. And actually this is local time, I'm sorry, this is the local time. So you can see that actually not like what I showed earlier for the CMAP model, for the single column run, we do see some of the models can capture the nocturnal peak. This is very interesting. Actually, we are going to dig a little bit depth in this to see why, this is the case. In our preliminary understanding is, those nocturnal peak is usually associated with elevated convection. So if model has the mechanism that can treat the middle level convection, there is a good chance for them to capture those peaks, such as, we modify the E3SM triggering condition, allow the partial launch level above the boundary is able to capture that. And also for the Korean model, they also using similar approach for the launch level. But for the Canadian model, actually, they specifically have a middle, a treatment for the middle level convection. So those models actually, this gave us some idea, how you can capture those nocturnal elevated convection at night over the STP side. The similar things actually showing at the Amazon region, but most models still have the problem, like trigger the convection during the day, specifically for the nocturnal precipitation days. You can see most model, peak in the early morning between 9 a.m. to 12 p.m. So those are something actually, when we put all the models together in the same picture, really can give you some idea, what the area you probably can put more emphasis on. So after you know what kind of parameterization they use in their model. So this is a multi-year project. We are still welcome participants, particular for CRM, LES, and the GCM models. So if you are interested, please contact me and also my co-chairs. We developed a homepage for this project. You can also get more information from this through this link. Yeah, so I only have one more slide. Actually, it's not relevant to the gas. It's some comments on the organized group modeling activity. This only from my point of view, and also try to have the discussion we will have in the second part of the meeting. So like Anne said, actually I agree with what Anne said, already. I just want to be brief. I feel that actually doing those kind of organized group activity really provide a platform for scientists to interact and collaborate on some important issues they are interested, specifically with weather and climate model. And also can provide a benchmark for follow up individual or collaborated studies. This is really a great way to facilitate use of detailed field content data, such as very useful data observed by the ARM program through the process level study, and also promote the use of common procedures and the data format to initializing and forcing process modelers. The problem for this type of study, like listed in ends, actually sometimes, it's hard to get participants actively involved. In most cases, actually, participants just simply passively respond to what you ask them to do. They won't actively get involved, so you have to think about a good strategy to get them involved in a more active way. And also the huge effort needed from the organizer to keep the project moving. Okay, that's it.
Thanks, Xiaosheng. There are a few questions. First of all, when you say that there's no clear improvement in diurnal cycle of precipitation with increasing mole horizontal resolution, what is the range of resolutions tested to arrive at this conclusion?
Oh, this including those model resolution tested in like the convection permitting resolution like 3 to 4 kilometer. Okay. So this actually is something we learned from the Diamond project. This is an ongoing international high resolution modeling intercomparison project, and based on some preliminary analysis performed by CMR, Leomore, and he found actually some model does show some improvement, but also there are a lot of models still have the problem in simulating the diurnal cycle precip. It's not like when you increase model resolution, you will get the improved diurnal cycle. That's definitely not true for all the models, at least for most 50% of model, I guess.
Okay, thanks. And another question, it's basically two questions on the same topic. When you talk about precipitation rate, for example, in slide 8, is that surface precipitation rate? And another question is whether did you calculate the fraction of total rain that comes from the large scale rain for each mole?
Yes, we did. Actually, like because I showed the figure too quick, if you can see, we did separate like the total and the convective. In this way, can tell you, we definitely look at the partitioning between convective precip and the large scale precipitation. And also try to separate it and understand, because some of the time, actually, when you drive single column model, they can give you a better result, but mainly from the large scale because it forces the model to respond in this way. So actually, that's why we want to do the multi-year simulation. If for case study, the is too sensitive to the large scale forcing.
And were these precipitation rates surface precipitation rates?
Yes, there's a surface precipitation rate.
Okay, thanks. We'll keep. I see that there are a few more questions. We'll keep them for the Q&A.
Okay.
Thanks. So me and Bobby will tell you about EMC Square, which is a new open source community framework for comparing column output from large scale models with ground-based remote sensing measurements. We know that there's an inadequate representation of cloud microphysics process as well as microphysics in large-scale models, and we typically use observations in order to evaluate these models. We typically want a direct comparison, or what we often refer to as apples-to-apples comparison with the observations. However, the issue is that remote sensing observations do not retrieve some microphysical quantities and suffer from detectability constraints. And there's also resolution differences between the field of view of ground-based measurements in this case and the grid cell size, the grid cell dimension in large-scale models. And for that reason, various Ford simulators have been developed for different purposes in order to bridge this gap between observations and models. However, we do have we should acknowledge that large-scale models continuously evolve. We can treat them as moving targets. And therefore, we need a flexible and easy to implement fast evolving framework, in this case for ground-based instruments, that will be able to keep up. And a community open source framework is such an example. So the EMC Square is an open source offline framework for large-scale model observation comparison. We can use it offline because we compare it to ground-based observations, which are not as demanding as, for example, comparing with spaceborne observations. Now, this framework is fully written in Python, which first of all makes it easy to integrate with NetCDF datasets, and Bobby will tell you about it in several minutes. And it also makes it basically easy to implement. And this relates to what both Xiaosheng and Anne have mentioned regarding overhead and the amount of work related to the participants in intercomparison studies, for example. Now, EMC Square includes a subcolumn generator, which means that we effectively emulate a higher spatial resolution of them all by translating cloud fraction into hydrometeor containing in hydrometeor-free columns. And we do that, and we use that to perform some forward calculations for ground-based instruments, which allows us to do some statistical comparison between the observations and the mole. And the idea is to match the physics implemented in large-scale models. We wanted to minimize the amount of physics or internal or implicit physics we basically use in these forward calculations. For example, currently EMC Square is fully compatible with the MG2 scheme. That means, for example, that if we'll take the column and generate these subcolumns, we would be able to see some horizontal subgrid variability in cloud liquid water, for example, which is part of the MG2 scheme. So I'm showing here an example for an SEM case study from AWARE. This is what Anne has already, the same case study that Anne has already shown previously. It describes the quasi-Lagrangian formation and evolution of a highly supercooled drizzling cloud in an initially stable atmosphere. So basically, we can think about the mole column as it sort of like propagates towards McMurdo Station. It approaches McMurdo Station around at 10 UTC, 9 hours of simulation time. And this is where we compare our Lagrangian SEM simulation with 1 hour of Eulerian measurements from a ground-based site. So basically, we have here a trade-off between the observational temporal resolution and the mole spatial resolution, which we increase effectively by using the subcolumn generator. And this is an example. These plots were generated using the original MATLAB development code, which parts of it are still being ported to Python. This is an example where we used the NASA GIS mole E3 SEM and compared it to the observations. In this case, we can see the AGSRL. On the left, we have the observations. On the top, we have the backscatter cross-section, while at the bottom, we have the linear depolarization ratio. And we can see on the right, the simulator, when we specify that we want 100 subcolumns. So one of the things we can notice here is that there's already some shortfall in the macrophysics implemented in the mole because the horizontal variability in cloud fraction, vertical variabilities, is not as sharp as in the observations. And we can see another difference here, which is basically higher values of backscatter cross-section in the mole in comparison with the observations, which may suggest some deficiencies or some differences in the droplet size distribution that we receive in the mole output compared to the observations. But generally speaking, we have a lot of similarity between the observations and the simulator. On the right, we can see here the mean and standard deviation profiles, which we can compare and perform some statistical analysis and do some additional calculations, for example, phase classifications and so on. Another example for the Kaiser, On the top, we have the equivalent reflectivity factor. At the bottom, mean Doppler velocity, or reflectivity weighted fall speed in the case of the simulator. And again, there's some overlap, and we can perform our statistical analysis. So Bobby, you can take over and talk about the actual software of EMC.
Okay, so basically, what the Earth Column Model Collaboratory is. So basically, it is Python software that is used to manage both the plotting of the observations and as well as generating the subcolumns and radar and LiDAR simulated parameters from the model data. And several features of it are going to make this. What the hope is with several different features that EMC Square has makes it to be something useful for the community to use. First of all, it is going to be easy documentation. It's going to have an automated documentation builder that is based upon documentation strings that are in the Python code that is going to make it towards easy to build the website so that everybody can look at examples of code and how to use each of the techniques that are on there. It's also going to be, it is implemented with robust unit testing procedures. So basically what this is that when somebody submits their code, if they're implementing a significant new feature, they have to implement what's called a unit test. And this unit test ensures that the code that they are doing does what it intends to do. And this test is run every time somebody submits a change to the code, so that just in case there's an upgrade to some software or that it depends on, we want to make sure that the code is still running as we submit more and more changes to it. And that's what this unit testing does. There's also I will go into a little bit here, but there's an expandable structure to EMC Squared that will make it adaptable to a variety of models and sensors. Right now, we have support for GIS Model 3E output, but it can be easily amended for E3SM, CAM6, etc. And right now we have the Mies scattering lookup tables and instrument characteristics for the HSRL, Ceilometer, Raman LiDAR, MPL, Kaiser, and Wacker. And if you want to take a look for more information about EMC Squared, I invite you to look at the link at the bottom of the screen. We'll move, next slide.
Can you basically change it to your screen share?
Probably could.
It will be more comfortable, convenient.
Share screen.
Great.
So what I want to get into next here is just some of a flow chart of the structure of EMC Squared. So first, what you start with is what we call a model class. And this data structure stores all the relevant information from the model that you're doing, including all the information about the variables and including information about the cloud coverage statistics and microphysics parameters of the model, as well as the density of scatterers, the terminal velocity of scatterers that are assumed in the different forward scattering calculations for the model. So what you do is that you customize this for your different model, and then what we do is use a technique called class inheritance to make a new structure from the model class and make it the model E class. And then we feed this in to the subcolumn generator and what we do here is allocate all the hydrometers to the subcolumns in order to simulate the subgrid variability within the GCM column, so that we can have our cloud coverage statistics and microphysics that is necessary to develop the simulated radar and LiDAR statistics. Here on next, for the subcolumn generator, we introduce another class called the instrument class that stores the instrument characteristics, Mies scattering tables, and instrument data here. And we customize this for your particular instrument. So for example, if we have Kaiser, we put on the Mies scattering tables, wavelength, all the different metadata information for the instrument, and it feeds a class called Kaiser. And then these two, the results for the subcolumn generator and the Kaiser class Kaiser instrument are fed into the radar simulator that give you radar reflectivity factor, Doppler velocity, spectral width, optical depth, and extinction for the simulated radar or LiDAR, depending on what your instrument you wish to simulate is. Finally, after we get these results, we are able to feed this into the do a comparison using toolkits such as the Atmosphere Community Toolkit that is developed by those of us here at ARM, as well as X-ray matplotlib wrappers, and as well as doing different visualizations with this toolkit. And I want to go through just a quick example of a Jupyter notebook of how easy it is to get this up and running right now with the Model E data. So first, you start just with your regular imports of the libraries of EFC squared, and as well as a few other Python libraries that we want to use. And then we load the model here by simply specifying the path to the file, and then simply do my model equals model E equals this. Basically, we'll know this model E class and point it to the variable here. And then we do the same in the HSRL for the instruments. Next, if we want to do what EFC squared supports is actually generating these subcolumns in parallel. So you can have the option to set up a parallel cluster using what's called the Dask toolkit here. And here I'm doing so right now. I'm setting up a 2-worker cluster here on the machine. And this can be expandable to HPC if you wanted to do thousands of subcolumns and do this for thousands of data points. So one of the good things about EFC squared is that it's also scalable to a HPC machine so that you can generate these simulations for large climate simulations. Next, we run the model here by just simply make simulated data with the model, instrument, number of subcolumns, and whether I have a flag here telling you whether you want to enable parallelism or not. And then the end it puts out into this data structure, which not only stores the original model information, but all the subcolumn generated variables as well. And then we could do some simple visualization of our results. So for example here, I'm just taking an example where we take an hour of one subcolumn of the optical depth from the LiDAR for the Model E case, where we are plotting the optical depth as a function of height on the y-axis and time on the x-axis. And you can see here, it's easy here to make quick visualizations of your results as you go in and look after you have generated the data. So in summary, a framework is required for easy apples-to-apples comparison of large-scale models with observations. And using LiDAR similar code applied to Model E and Kaiser HSRL, we used the radar similar code applied to Model E and Kaiser HSRL example from the AWARE campaign in order to develop EFC squared. And EFC squared is currently in development, provides an easy-to-use, well-tested, well-documented framework for apples-to-apples models observations comparisons. And we're going to future plans include expanding this to support a variety of other climate models and scanning radars. And if you're interested more in learning how to contribute to this, you can either contact me at rjackson@anl.gov, or you can contact Israel, as well as you can go to this website here to look at the GitHub page of EFC squared and look to see how you can potentially put in your own code and your own pull request as a contribution to EFC squared. So I would like to stop it here and open it up to questions.
Thank you. So we have a couple questions here, and I guess I'll just kind of throw these out to you, Bobby, and Israel, and thanks for a great presentation. From Michael Vitta, is it possible to adapt the subcolumn generator for different subgrid variability assumptions, e.g. different PDFs or scale awareness?
I would say, yeah, if you want to do a different PDF, that would definitely be possible. I mean, right now it just assumes a random assignment. But if you wanted to change the logic between if you wanted to just change, for example, if you wanted to bias it towards one part of the subgrid or another part of the subgrid or different subcolumns and do a different distribution, I could definitely see that being expandable.
Yeah, so at the moment it fits the MG2 scheme, which basically means that we assume subgrid variability corresponding to gamma distribution. But definitely, this can be added if we wanted.
Okay, thanks. Katya Lemaire asks, any plans on implementing a different scattering lookup table to improve the representation of non-spherical particles? Perhaps having different scattering formulations could allow to run the forward simulator in an ensemble approach like done in her GoToSim, which is also designed for Model E3, to provide a sense of the uncertainty. Stefan Kneifel says, I wanted to ask the same question.
Yeah, I mean, pretty much as long as we're able to generate, well, it wouldn't be me scattering for ice, but for example, if we wanted to improve it with some T-matrix assumption or some other scattering table, for example, from the Brian Baum paper, as long as we have as long as we have the radar scatter cross section as a function of size for differing particle habits, I can see potential for expansion.
Yeah, and I would add that on first order, our main objective is to use that for large-scale models such as climate models, which, to my knowledge, still only work with spheres. Please correct me if I'm wrong. But because of that, at the moment we just work with Mie calculations. But again, yeah, there should be the option if you want to add for spheroids, etc.
Yeah, and I'll just comment, it's one can use different scattering assumptions. I think it's always a question, how to learn from this exercise, because if the fall speeds are those of a different ice type, what does everything mean? And I think we have a lot to learn in that area. So
yeah, I mean, it's going to be very uncertain. I mean, it's very dependent on your ice crystal shape, as far as what type of reflectivities or velocities you'll get out, or lighter back scatters you'll get. So we'll have to, that's definitely something just assessing whether we aggregates or dendrites is going to be a big challenge in itself.
And I think that uncertainty is a really big issue that we want to dig into, that Katja brings up. So Philip Grivank asks, would it be a lot of work to enable LES comparisons where the subcolumns could be randomly sampled from the LES columns?
It doesn't sound like it'd be that much work. I mean, if the subcolumns are the LES columns, it wouldn't be that much of a change.
Okay. And Steve Klein, speaking as a developer of COSP, EMC2 looks like a great simulator for comparison to ARM remote sensing instruments. While it appears to have a lot of nice features, the hard part is how you can adapt to a particular model's physics assumptions. This requires good documentation. Israel, I know you've worked hard to fit this to our physics assumptions. Do you have any comments on that?
Yeah, so I agree regarding good documentation. So therefore, we wanted to be very thorough when developing the code for the EMC square. I agree that adding completely follow the internal assumptions of the model would require some literature survey of basically documentation of these models implemented in these models. But I think that it will be a relatively straightforward task in this case.
And that's why.
Go ahead, Bobby.
That's why when I asked for a contribution for a pull request in terms of any major features like a new model or a new instrument, I'm going to require that the user document and reference all of the assumptions with regards to what model assumptions are being put into calculations of the fall speeds or various LiDAR ratios for different particle habits that go into these calculations.
Yeah, and Susanna Burrows asks a related question. Just want to note that my recent experience in conversation collaboration with Katja and Polen Ma suggests some mods in the E3SM code itself would also probably be necessary to get the required info out of it and make sure it's consistent with the assumptions made in the forward simulator. Have you been thinking about this already for your code? And I would say the answer is yes. And my answer to Steve about requiring really good documentation. To be honest, I personally feel like if you're not working with a developer who knows their code really well, it's extremely hard to get a hand-in-glove fit with the simulator. And one of the things we hope with this open source community code approach is that each group, if they want to participate, they can get some help making, basically making that connection, at least at the code level. Of course, they still need to get this information out. And I guess I wonder if Susanna means modifications to the, not the physics of the code, but more the code itself, just to report some additional things. So anyway, good question.
Yeah, from my experience, it was also very relevant for the macro physics, because typically when we discuss the microphysics, we just mentioned a microphysics scheme. The macrophysics are a little bit more tricky here.
Yeah, great point. Peter Caldwell asks, what are the benefits, drawbacks to implementing using a new instrument in EMC squared rather than COSP? It seems like COSP could accomplish EMC squared's goals as well.
Bobby, or?
Well, I think the major benefits, first of all, for putting it into EMC squared is that just having the framework, being on the open source and being on GitHub, just having it there is going to make it to where contributions are not only going to be really easy to do, but also they're going to be well documented and also being able to be well vetted by the community and reproducible. Versus, I'm not sure what the situation is with the ARM simulator, but I know at least with EMC squared, that is one advantage there. Another advantage there too is that we have support for parallelization on HPC clusters. So if you have a very large model simulation, you can actually generate these parameters for scales that we require, for large scales that we require the data to be generated for.
Mm-hmm.
I think that also the code is effectively relatively new, so therefore it's thinner, and again, it's fully written in Python. It's easier to digest on what's in there and what's not.
And also, with the unit testing requirement, we are requiring that every significant contribution be able to have a unit test that's run every time the code is submitted. So if a new version of Python or a new version of MATLAB or Matplotlib or something comes out, one, we'll know if the code breaks and we'll be able to fix that immediately. Two, we'll know if any contribution comes in. We'll know if you're breaking the code or not, just because it will fail our tests.
Yeah, I'll mention just, those of us who just worked in development with Model E3, fitting the COSP assumptions to our physics is non-trivial, and we haven't been confident that we've been achieving that so far. And I'm a little bit of an outsider to that effort, and I guess some people are running COSP offline, some inline, and yeah, I'll be able to answer that better after we've gotten a little further. Thanks. So Stefan Kneifel asks, regarding the scattering properties, I think key is to be consistent between the forward operator and the assumptions in the microphysics. It's a topic we're discussing here. If the model assumes dendrites, mass dimension, fall speed dimension, and the forward operator assumes soft spheres, differences are unavoidable. Good comment. All right, so I have a few discussion, maybe, let's see, I have a few chat here. Samson, had a question about Xiaocheng's comment on active participation. And I'll leave this to Xiaocheng while I bring up some other questions. Samson asks, Xiaocheng, you mentioned lack of active participation. Could it be because people are not funded to do the intercomparison work? Would it make sense if there were funded tasks from the outset?
I think the main problem is the people are not funded for participating in this type of things. Specifically, if we ask too much, like you mentioned, the output, all those details, they may feel they don't have the energy to really work on it.
I mean, we did have a CMDV program for a few years there. That at least, so there was some more activity when that was going on, and I think this also does I think we still need to have some program like that to keep going on with an effort like this, and this highlights the importance of it.
Okay, and Steve Klein had a question here, and I'm going to, let's see. So I think Steve, do you want to ask your question there, or comment actually about COSP, the GitHub site and so on? You should be unmuted. So it's a little hard for me to show these. Israel, can you watch the chat and the, for me?
Yeah.
Okay. All right. So I'll just start Steve, let's come back to that discussion in a minute about COSP. So first, I guess our bigger question here is, and we could spend, let's see, we have about 45 minutes. And Sally, can you remind me how, and I'll ask you to handle this, Israel. Sally, can you remind me how we can let people talk from the participants? Do they need to be promoted to panelists?
No, you should be able to unmute them. So if they want to talk, they can raise their hands, and then a co-host should be able to click on allow them to talk.
Okay. Okay, good, thanks. I think Steve might not have audio connection, so, okay. So is there, the big questions here are, well, we think is there a need or a desire for more organized modeling activities within ARM and ASR? And Xiaocheng and I, we miss the modeling working group that used to exist to some degree. And we wonder if there is some role for a model-centric focus group that could be about organized activities. The GCSS activities were usually, but not always, focused around IOPs. And so we're wondering if there's an interest to expand the focus beyond IOPs very explicitly to harness long-term, and that includes AMF statistics relevant to, climate relevant cloud physics and aerosol physics. That kind of actually, the sky's the limit there. And third, could a group like this support multiple diverse activities with any number of participants? So the things we're doing at GIST right now, we want to make it possible for others to participate with us, and whether that's one group or two groups or more, that would, we could imagine a lot of activities happening at once, but sharing some common frameworks that would lower the bar for participation in, all of them or just a few of them. So, overall approach, we discussed the one possibility, this pairing of LES and SCM case studies. And yesterday at the LASIK session, we discussed possible pairing of oracles and LASIK. And all of these could have reusable, so to speak, reusable elements, such as the common LES SCM framework proposed by the French groups to lower overhead on participation. And we discussed these elements. So, of the LES SCM unified framework. And yeah.
We have two people who wish to talk. First of
great,
all, I think this is Steve here.
Okay, great.
Can you talk, Steve?
I can, but I was going to wait till Anne was done with the slide. There's no need to interrupt Anne at the moment. Thanks.
Okay. And
oh, well, go ahead. I'm really done. I'm just, I'll just leave this up here. And I wish I could see. Go ahead, Steve.
Oh, I was just going to comment on this. Why don't you finish the slide, Anne? This is the general framework I think we needed to be discussing. So, yeah.
Okay, good. Well, okay, so the elements that we discussed so far, just to repeat, are the LES and SCM. That's powerful, and a lot of groups are, including us, are using that for lots of things. The second element could be this open source, in the case of ARM, a ground-based simulator codes, and the ARM has one. We're working on one that we really meant to design to ID cloud phase, but actually some of the statistics we're looking at right now, we're using soundings to identify phase. So it's, the existence of supercooled clouds. So it's, I'm not sure exactly, the simulator could take different forms. And third, use of ARM computational resources to support model obs evaluations, including the long-term statistics. So I have just opened it up to the floor with kind of a thought to these high-level questions too. Go ahead, Steve. Thank you.
Yeah, I just wanted to talk with the group about some of the conversations Anne and I had in preparation for this session this morning. And, you know, I'm mindful of the overhead involved in organizing community efforts, but one thing I was thinking about is, you know, in lowering the barriers, as Anne is talking about, one thing that could be helpful is if we have ways in which people can make contact that are easier than, especially now since we're not together in person. And one of the ideas I had was, rather than a big organized effort, maybe having a bulletin board where people would list things and connections they're seeking, and then also people who have tools to share or things that they think others might be able to use could post things that they have available for others to use. Just to give an example, in our own case, we were interested in using the MAGIC data from the ship that went from Los Angeles to Hawaii to compare to E3SM simulations of low cloud. And we wanted to use a forcing for the single column model that Chris Bretherton and his group had prepared at University of Washington, and they'd also done the LES data. So we had gotten together and formed a one-on-one collaboration. Of course, that's very easy to do, but it was nice that they were open and willing to collaborate with us. But I think if we have a collaboration, you know, place where people are sharing things or saying, we're looking for this, does anybody have something to help us out with this? This might be a helpful way to get grassroots organization and facilitate collaboration and use of data and modeling exercises. So that's all I wanted to say.
Thanks. I love the bulletin board idea.
There's Thais. I hope I pronounce it right.
Thais?
Yeah, you can speak. Just unmute yourself.
Yes, that's close enough. First of all, yes, I miss a good modeling group too, especially now since we're online and can't, you know, do our discussions in the hallways with different modelers and different people. And I think we actually potentially have a pretty good framework in ARM ASR to have a bunch of collaborations into comparisons, given that we have a whole bunch of lasso cases and a whole bunch of, we have the variational analysis and ARM best estimates, et cetera, And based on those, we could easily, and I guess the precipitation diurnal cycle approach is kind of doing that. Just, you know, if we have a couple of people who are interested in modeling those kind of cases, all we need is to agree on, hey, this is a research question that some subset of our modelers is interested in tackling together. And that could be a relative, once the framework is set up, that could be a relatively easy turnaround there. Yes, bulletin boards are nice, I think. But they also, that's yet one more place where I have to look if there is the occasional, only the occasional activity, I probably will forget about it. One thing we had, especially responding to Steve here, one thing we had a couple of years ago at least were a couple of virtual meetings that I massively enjoyed, and maybe this could be the type of topic to do some virtual meetings, aside from the larger ASR meeting as well.
Thanks, Thijs.
Also, Michael Whitty and Lulene wanted to talk. Michael?
Yeah, thanks. I'm actually going to take the opposite perspective of Thijs. I think the bulletin board is great because then if there's something I need, I can go out and find it. And I think actually this ties into Steve's comment as well, where we've been wanting to work with MAGIC data. And one of the things I've been concerned about is that there could be this proliferation of different forcing data sets that end up emerging. So I think it would be really helpful to have a central repository where we can access a forcing data set for whichever AMF deployment or long-term site. And I think that the DEFI format that you mentioned, and I was also part of that workshop, I think that would be really fantastic, so that regardless of which method is used to generate a forcing data set, whether it's lasso or variational analysis or some PI generated reanalysis based data set, that we can have one single format to go and use to drive our models, so that at least that ambiguity is removed. Because I think that's going to be a big issue in understanding the results. If everybody's got a different way of setting these things up, then how do we know that we're actually comparing apples to apples? So that's my 2 cents, and I think it would be really great to see some more forcing data sets come out for projects that maybe there's not going to ever be some large scale intercomparison, but because of whatever the context of that project or that AMF deployment is, et cetera, some PIs have interest in that. So it'd be great to kind of elevate that and maybe automate the production of those forcing data sets so that it doesn't require 15 different people wanting to use it.
Right. Thanks, Michael.
Lulin?
Hey, thanks. Anne, could you put your slide back? It seems like it's not on show. But
Sure.
thank you, Anne. Thank you, Xiaochen, Israel, and Bobby for your great session this morning. And I actually participate the DEFI workshop for a very short period, and I actually probably heard Anne's talk, and also Graham Fur from our group in NCAR. So at NCAR, we actually have developed a CCPP SEM, so the Common Community Physics Package framework, and then the SEM can actually use this framework to actually have the interoperability to change physics within that framework to test different physics packages. And here I noticed that, Bobby, for your ECM EMC cube development, that have the similar kind of a philosophy behind it. And it's actually very good direction that we want to make even the output and observation comparison a little bit more interoperable. And that way, if you really submit your results in, but with certain metadata, and you're able to actually kind of process the output and hook that with your forward simulator or different observation comparison, that really kind of lower the bar or I would say enhance the capability for groups to participate. And I do concur your first red items. I think we really want to have a modeling-centric kind of a group to really span the hierarchy of the models to make sure that the different tools and different approaches can be also kind of joined together and discussed, and with the long-term data to verify or to validate our approaches, that would be super valuable. And I think Mike's question or suggestion is also along this line. It just try to make things easier for participants that actually will stimulate a lot of new ideas and collaborations along the way. So yeah, it's kind of a. Also, I really hope this would take off and then have more discussion among the community. And especially, Xiaochen, your hierarchy approach is exactly what we are proposing to actually test the operational forecast model to really ID the issues in the physics and to improve the model along the way. So we have the same goal, and it's really great that we can actually share experiences and improve each other's capability. Yeah, so that's kind of my thoughts along this session, and I'm really happy to see everything happen. Yep, thanks.
Thanks, Lulin.
Roy Merchant wanted to speak, but I don't see his hand raised anymore. So if you want to speak, please raise your hand. Oh, you're there. You can speak. Just unmute yourself, right?
Yeah, I see. Right, so I think a lot of good points have been made here, and I am very supportive of having, I guess we're calling it a bulletin board, but I'd call it a web page, where a lot of this can be linked together. But I'd also like to back a couple of the other points that have been made. I think Theis's point was not that he thought the web page was a bad idea, more that it has to be more than a web page, right? And part of what made GCSS exciting and interesting was their meetings, right? And putting together a lot of the results. And it was very interactive. It wasn't somebody decided to have an experiment and set it up and then lots of people flocked to it, right? There was an interaction. A lot of the time, these experiments had several phases they had to sort of cycle through before they could figure out exactly what they wanted the forcing to be and exactly how to configure the cases, right? So that has to be a sort of a moderated activity. And that's in part why the lead person was so important in making that work, right? It's not something you can do on a 3 months of your time kind of basis, right? It's a major effort to really be leading one of these activities. And part of that, you know, I also agree with the point that having tools that's been made here that would be more easily universal is a great idea, but that's not going to be a replacement for having a human interface there who's really actively taking data from people and putting it together and trying to pull the science results out and doing that interaction, right? So I just want to sort of tie a number of these points together. So web page is great, but it also needs a strong leadership, which has to be supported in some way. There has to be meetings and there has to be a cycling process that goes through to improve it over time. And in that sense, I agree with the comment that you made offhand, Anne, about MPACE being revisited. I think that would be an excellent thing to do. And that's the kind of thing that really requires a lot of long time carry through to make happen. Right. Anyway, those are my thoughts. Thanks.
Thanks, Raj.
Makina Stanford, you can talk. And afterwards, Susanna Burrows.
Yeah, great. Thanks for these presentations, guys. Regarding the pairing of LES and SCM cases, there was a very active discussion yesterday about the setup of lasso cases for the cacti field campaign. And you're not going to get, of course, incredibly long-term observations. Those will be focused more towards IOPs. But it'd be worth considering this specific group collaborating with Bill and Andy and Adam in the setup of those LES cases that they're planning on doing so that we can leverage the SCM simulations as well. Yeah, just something to think about.
Thanks.
Susanna?
Yeah, so I just thought I would repeat something that I've already said before to Anne, which is that, you know, wearing my hat as someone who spends part of my time working on modeling and building better models for sources of aerosol that contribute to ice nucleating particles, I frequently get asked to basically calculate in the model what the climate sensitivity to those aerosols is. And I think that's something where we really just, currently global models are not at a state where we can really have confidence that they respond correctly to that. And so I've been really hesitant to do this kind of thing. And this seems like, it's really encouraging to see the progress that's been made on LES simulations, and but still it's sort of past studies that have this huge diversity of results from LES then also makes it difficult as kind of an outsider to that community to figure out what to believe. So having like new intercomparisons to show how the current generation works, I think to me, that would be really a helpful thing to see. And then I just wanted to also add another comment on this last slide. I see you've been thinking about this already, but I want to reinforce this point, or kind of add my 2 cents to this point about pairing the LES studies with ESM evaluation, because we do see kind of all over the place examples where models that have been developed primarily with benchmarking against local site data, once they get extended to the full Earth system model globally, don't perform as well as expected. And the model that performs best at the site data, even if it's many sites that have been carefully selected, sometimes is not the one that performs best globally. And this is something we see over and over. And so that pairing with actually having a plan to, at some point, include the ESM evaluation, I think is really important, and I want to reinforce that point.
Yeah, thanks.
Now, before we move on to Andy Vogelman, who also raised his hand, I see that Hugh Morrison commented, I strongly support Steve and Michael's suggestions for a bulletin board linking case study data for individual modeling groups. The bigger barrier to large, small intercomparison is finding someone to lead this effort. This is arguably much more than a barrier than getting participation from individual modelers. If smaller groups can work on this rather than the big top-down effort, perhaps could get more mileage out of these cases. And Marcus van Leer also added a comment that I foresee these efforts as directly informative on GCM model tuning. Thus, the applicability is very broad, and efforts will reap huge benefits for many.
Thanks.
Andy Vogelman. Andy, you can speak.
Yeah, thank you. Yeah, so first off, thank you very much for putting this session together. I think it's always been something that's been bugging us, how to make better use of the resources. And I think it's also timely too, because there are different things coming into the picture at this time. Sort of following on with McKenna's point, you know, right now LASSO has, well, LASSO is here. Okay, and so some of the things that you're talking about here, already quite a bit of effort has gone into at least doing a first cut on these data sets within certain restrictions. You know, remember that LASSO is you know, sort of meant to be the first cut on the data, not the PI cut on the data, but basically beating the path, if you will, taking care of, frankly, some of the most time-consuming efforts, like, for instance, vetting forcings and things like that, for the benefit of others. Now, as I think most people are aware now, LASSO is transitioning from shallow convection, where we were operating in a quasi-continuous mode for a number of years, to now focus more on IOPs. As McKenna mentioned, yesterday we had the cacti session. We're focused on that. We're spinning up on things there. But after that, and in the next fiscal year, we are going to now be pushing into the ACNA data set and looking at marine boundary layer clouds. All of these efforts, you know, like I said, we are going to be, you know, doing the heavy lifting, if you will, from the standpoint of the forcings and things like that. We always will be benefiting, especially as we move in from regime to regime fairly quickly. We were going to need area expertise. Also, I would say area retrievals, so to speak. This can be sort of a focal point. Because the ARM retrievals serve as our backbone, but we definitely would benefit as well from PI retrievals. So I'm sort of seeing that I could see how LASSO could you know, play a role in something like this. I don't, you know, we have finite resources, but my point is that I see that some of the pieces are sort of already falling into place. This is focused on the IOP part, and not to necessarily the long term outside of the shallow convection. But it's an interesting idea. I'm still trying to frankly get my head around this, because honestly, the problem that you're addressing in this session is really big. It's way beyond everything. And as you know, you and I, Ann and I know, working on the Recoro data sets, you know, that was a humbling experience. You realized how many things are really involved in pulling this stuff together. But I could sort of see, by making things a local focus, if you will, for a short period of time, that because it's short term, we may be able to involve people more readily. We get bumped up on their priority queues enough so that you can really make headway. But I think it would take some sort of partnership, if you will, with some other people to possibly make that work. So that's just a rough idea, but I wanted to get that out there. So thank you.
Thanks, Andy. And I want to just really commend the Lasso website and the work you guys have done massaging those data sets and making them accessible and all your metrics. It's a really fantastic resource. I can't wait to see the cacti cases. So thanks. And let's see. Are you watching the hands here, Israel? I'm seeing some up, but I don't know which one up first.
Mike Algrim, you can talk.
Yes, hello. Yeah, so discussion and presentations, thank you. One thing I want to mention is I think it's actually good to have a mix of two things. On the one hand, trying to get the modeler group together to talk about projects and getting them to work on one particular thing as a focus group. But on the other hand, I think it's also really important to have something like easy shop, if you like, for cases for modelers who don't have a lot of time, don't have a lot of overhead. So this DEFI format, for example, I think will help a lot for those who don't have that time to get involved in a big intercomparison project, but who still want to use some of the observations, some of the data sets and foresights and so on. If it's less overhead to get into it, then I think more people will participate in their own time. So for example, the ARM case is still around and is still being looked at. So that's one of the SGP cases from ages ago. Mm-hmm. And even though there's now Lasso and many, many more cases, some people will go back and revisit that anyway. And I think if we had a single format, easy way to find these cases and look at them, it would invite a different kind of modelers maybe who just don't have the facilities to participate in something more involved. So I think having these two streams going in parallel is great.
I like your point. It's kind of not either or. Thank you. I see Philip Grivonk has had a hand up for a while.
Yeah, yeah, you can talk.
Okay, hello. So what I wanted to say is actually follows quite closely. So I've been working a lot with the Lasso data, and I find the amount of work and effort that's gone into preparing all of this very impressive. And the sort of the missing cherry on top would be the ability sort of to grab it, run your single column model over all the 100 days, and then to plug your results back into the default evaluation, so that you can really say, and I think this is something that could happen still many years from now. So you have an idea, and then the first thing you do is you say, let's run the 100 Lasso days, so that you take that and then sort of ideally maybe something like what was showing with the EMC2, you sort of download the Lasso package, run your days, and then it chucks you out the 10, 15 measurement comparisons they already have in there with the possible option of comparing it to the some of the other reference ones. And I know it's easy to ask for something like that because I won't be doing it. But I mean, I think that really is sort of, there's so much there already. If you could sort of add this ability to plug your results back in to do a one-to-one comparison to what has already been done, that would be very nice.
I think that would be great to, you know, I mean, it occurs to me, again, if there were some open source code, you know, especially, and an easy way to access all the results. So the plotting and everything else, you know, all that front end work is made much easier. So that would be great. Thanks.
Andy, do you want to comment?
Yeah, actually, had we had the full meeting, we actually had a Lasso session planned. And part of that was to do we're working on getting this type of capability out there. So basically getting I forgot exactly the terminology we were using, but basically sort of that plug-in capability. So this is something that we are looking to hold in the fall when we're circling around to pick up the other topics that couldn't necessarily be held this cycle. So stay tuned. It is something that we've been working on.
Thank you. Let's see.
Yeah, so Johannes wants to comment.
Hi, can you hear me?
Yeah.
Yes, we can.
Great. So I just wanted to amplify what Susanna said about, well, from first-hand experience, we recently did a study where it turned out that in our model, at least, the cloud lifetime effect was much more sensitive to the occurrence of precipitation rather than precipitation susceptibility to aerosols. And I think, well, I guess the point I want to make is if GCMs come into a comparison with observations, knowing what they're most sensitive to, that would help a lot.
That sounds really exciting to me. Yeah, and I really appreciate your recent work on that, your recent paper. Calling for kind of...
It's something that GCMs can know by doing PPEs or whatever.
Peter Caldwell says in the Q&A, I agree with Micah that having a big library of past cases would be hugely useful for model development. To amplify, I think having many models run the same case is useful for understanding the physics of model world versus real world, but having many cases to run with a single model is best for optimizing or tuning one's particular model for release. Yeah, thank you. Do we have any other hands raised? Don't be shy here.
We have some more comments or questions. I see a comment here. I'm a big fan of pairing LES-SEM with ESM using long-term observations at permanent sites. The bullet point on the discussion slide reminds me of the strategy that Christian Jacob, where is it, proposed a while ago for doing this. We adopted this method when configuring long-term SEM and LES at the site in the Netherlands, and it really delivered.
Great, thanks for that comment. And I just want to say, some feedback we got is, oh, you're not suggesting anything new. And that's right. I think we aren't suggesting anything new. But the part that isn't happening right now, maybe at ASR and ARM, is the sort of discussion that Raj is talking about at every meeting, as much as it used to. So, but yeah, no, this is well-worn paths that have really worked well, I agree.
Yeah, so this relates also to Paquita's comment that she agrees with Rod's comment that occasional get-togethers are valuable for developing and maintaining momentum. We will have, where is it? We will have one in the fall for the Oracle's LASIK activity, and mentioned the prior preparation for how to focus this in a meaningful way for the interested participants will be an important tool, of course. And I see a pretty long discussion. Marcus van Leer actually suggested, I don't have a good sense for how the forcing data sets are put together, but given the uncertainty in the forcing may be significant, I wonder if approaches have addressed the possibility of an ensemble or collection of equally probable or PDFs of forcing for a given case.
Yeah, I want to jump in there and say that's exactly what we did for Rocoro, that Andy Fogelman mentioned that we worked a lot on the observations, but the other thing we did is precisely this, and we used variational analysis. We extracted forcings from WRF with data assimilation on, and that is actually the Lasso approach that Andy, to some extent, it was adopted by Lasso. Andy could comment more on that, but they have an ensemble forcings also, and that is a huge source of uncertainty.
Actually, I also want to add some comments on the forcing uncertainty. So can I? So actually, for the variational analysis forcing, we also try to derive the forcing by perturbing some of the constraints we use, such as the uncertainty in the surface observed, turbulence sensible heat fluxes, and also the precipitation. This is the biggest constraint we have. So we try to produce the ensemble forcing. In this way, this can partially address some uncertainty associated with the variational analysis. We did this for MC3E. We also had this actually for the TWPIs. I think Christian Jacob's group is running the single column model using hundreds, forcing perturbed by, from the variational analysis method. So this is one thing. Another comment I would like to make regarding the case library. I have been promoting, to create ARM data category specifically, collect all those cases that have been widely used in multiple intercomparison study for the modeling work, So, but the problem I know is, one is, ARM want to, all the cases can be easily found, so we have to put all the data stream in the ARM archive, like the production mode in this way. So my suggestion is probably we can do some like the symbolic link, we created those case library at the ARM homepage. There is a link there. They will list a list of cases people have been widely used and connect all the available observations, including forcing, evaluation, and some detailed ARM observation, like from radar, LiDAR. Those people would like to be interested, but put some symbolic link there. People click there, they can go to the ARM archive to really get the data, but at least they have one-stop shop. They know the list of things there. So I'm working with the ARM infrastructure team, try to make that happen. And also we work with the ASR SM single column model team led by Peter Caldwell and Peter Bogenschut. We provide all the ARM, forcing data, for maybe more than 20 cases there. Is standardized. Actually, people can go to the ASR SM single column model homepage. They actually click and get almost all the ARM forcing there, like a case. They're also well tested by ASR SM single column. That's some information there. I will stop.
Thanks, Xiaoqing. I see Marcus's hand raised. Before we go there, we have about 9 minutes left to our session. And so I'll just say, I think, let's see, I think there's a diversity of interest in engaging, with, say, rerunning MPACE or, doing, using long-term observations or whatever. I think what we'll do is ask for the participant registration list. ARM can supply that to us. So we'll email this list and with, any pickup activity, and if anyone wants to contact any of us, please do. And I'm with Raj that, the in-person communication is it's really helpful to me. And maybe some of us feel that way more than others, and, that's fine, I think. And of course, activities that involve less personal engagement are, the more that maybe I would suggest, maybe the more we can standardize those, the more it's in the way that Xiaoqing suggests, maybe the more easier it is for others to pick them up later. So, let's see, do we have, so I don't know if there's some, I want to highlight Richard Forbes's last question and his last comment, where he asks, LASSO is a really great initiative, which will hopefully address development issues. And he asks, what else could we do to enhance the value of LES for GCM parameterization development? And I think that's a great question, and I would welcome the chance to talk about that more in a follow-on discussion. Marcus, let's see, do we have any other final hands or final comments from the organizers? Or
so I just wanted to quickly say that if there is some standardized format for the forcing, then it'd be nice if that uncertainty was considered either via covariance matrix or a vector of variances or something like that. And yeah, the data assimilation or variational analysis should be able to directly input a covariance. I think that's what Xiaoqing was referring to. So that would be great. That would be really fantastic to see.
Yeah, I mean, I have to say, when we're doing our model development, we basically forget about the observations at that point right now, and we just say, now that we've got this LES that does our physics, can our SCM do that physics, that we're thinking about? So it's an interesting, it'll be interesting to talk about that further, I think. All right, Courtney Schumacher mentions Go Amazon. I think we have a lot of good AMF targets for long-term data. That's a good point. All right, well, I want to thank everyone for contributing and sharing opinions and spending their time on the session when I know everyone's got a lot going on. So you'll hear from us, some sort of follow-up, and thanks, Xiaoqing, and Israel and Bobby and ARM for hosting. Thanks, Sally.
Thanks, Anne.